Okay, so we're looking at filtering our training data with the scores that we have that we've saved from running our model over all of our available assets. So, got this script here, which is what we've ran before and what we were just working with. We're just grabbing in our scores from scores.to.json, and as we're bringing them in, we're processing them. And then here we're going through and looping through all of our birds, and then all the assets for all of the birds, and then all of the scores for all of the assets for all of the birds, and totaling up how many of those scores actually equal. I mean, they're not really scores, they're classifications. We're creating a score from it, from how many times that classification matches the index that it's supposed to. All right, so we're doing that here. And then here we're graphing that to see what's going on. So here's our first element of the array is the yes, and the second is the no. So here we're graphing all of the first elements, make them green, second element's orange, so we can see all the places that they actually do match and the ones that they don't. If we take away the ones that don't, we can see a little bit clearer the ones that do. So we have some that are pretty low, but maybe we can fix that again on another iteration and just include more files. Alright, so here we go. We're going to do the next part to where we're actually going to just go ahead and create the training data. So we're going to, same functions as we have been using, the download and wave with FFmpeg to create a mono 16K wave. Then create spectrogram, which runs the transform function from the new yuki.io code. So run that block. Here's our spectrogram maker. And just as before, this is where we're filtering to see if we're going to use the spectrogram or not. And that code is right around here. I'm just going to change one thing because we parsed these out into a list of ints earlier up, so we don't have to do that here anymore. Before we did that here. So anyway, score index is at -1. We're going to grab our asset scores, so just look in that scores dictionary for the asset ID values. Try to download it. If it doesn't work, we're going to sleep 10 seconds and try again to download it. And then coming up here, we read that using the scipy wavefile.read function. Convert it to a float and then a float 32. Just by dividing it by the max int 16 value for numpy, and then setting the type to float 32, because originally it's a float 64 when you divide it. Then we got create the spectrogram from that audio data using up to the max number of seconds available in there. Okay. And then here's where we're actually checking those scores. So we're going through each of our windows, and we know that the window here is 1/4 of the window that we classified before. So every 4 here, we need to look at the next score. So we're starting at -1, but if our window index is also starting at 0, 0 divided by 4 is 0. So that we increase our score index to 0. And then here at asset scores, we look for the score for the 0 index. And if it doesn't equal our bird index, then we're just going to skip this. Alright, so we should have a lot less training data this time, which gives more credence up here to setting our max files. Where are we at? Max files to 50. Because that's what we trained on. Speaking of, let's go back here real quick and see if there's a difference. I know this is a quick tangent, but we've been talking before about looking to see if there's a difference in the first 10 assets versus the later ones, because when we train this, we use data from the first 10 classes. So let's look real quick here. We're going to go from up to 10, and we're going to call those bird scores 10, and set here bird scores 10, and we're going to do the exact same thing and call it bird scores 11. Nice and creative. And we're going to be going from 10 up through 50. because we classified up through 50 here. So bird score is 11. And then let's print these two out as graphs. So we're going to do bird score is 10, bird score is 11, and we'll call them green and or yellow, green and blue. There we go. Okay, and so green are the ones that we could have overfit on. Blue's the ones that we shouldn't have overfit on, or we've never seen before. So blue does look decidedly lower. Yeah, so we're definitely overfitting some. So again, more credence that when we go back through, we should increase the amount of training data that we're letting come in here, and maybe we'll get better results. Okay, continuing back on. Here's our spectrogram directory, our getBird function, and then where were we at? Right here at the bottom. We're about to call this. So we get our items. We're just creating a bird items list, which is a tuple of the index of the item and then the item itself, which is a dictionary. Yeah, it has two keys. One bird, which is the name of the bird, and the other one's audio, which is our list of assets. And we grab that key right here, audio file item.audio. Anyway, okay, does it work? Looks like it's going. That's good. Let's see if it's creating stuff. Okay, we've got some spectrograms coming out. None there yet. Okay, now it already has some. So, suppose we can still call all this as part of iteration 3, and we're just going to call it step 2 of the sound event detection, which seems like it should be a 3-step process for this third iteration. Those 3 steps being first our 512 window, next this 196 window that we're training with data that's been filtered from the 512 window, and then maybe next we will do one more 196 window after filtering the data from this one. Or maybe we'll save that for the next time around, because so that way we'd have more training data to actually go in and use that with. Otherwise, it sounds like that's just asking for some extreme overfitting. But I don't know. We'll see. Maybe we should listen to some of the audio that's coming out of this and see what it sounds like. So a quick look at our processing. We got all 16 cores running. Yep, there they are. Python 3. Multiprocessing, parallel processing. We got some that it's having an issue on, but not too many. Maybe after this we'll go through and we'll graph the number of spectrograms that we have per class. It should be about the exact same graph as we have above, but yeah. Let's see, is there any way we can tell where this is at? Looks like we're still in the first 16 block. So I'm gonna let this run for a little bit, and then we'll come back and check it and see what it's doing. Okay, I think our training data has been filtered. If we go through and look, we got lots of output here. So let's see what it looks like. Just gonna grab a glob. We're gonna say 4 index in range 105. It's just our in classes. Let's just count how many spectrograms we have per bird. Let's see, so we want to say bird spectros, append the length of the glob of the data spectrograms index star.spectro files. We're going to throw in our index in there, and then we should be able to plot that. our range of 105, and then our bird spectros. Cool. So it looks like the graphs that we were seeing before, and it should. So we're making spectrograms of all of the portions of audio that have a class from our previous model that match the class that it's supposed to. All right, so what are we going to do now? We have all these spectrograms. We're going to make some TF records. Same thing we did last time. All right, let's see how many we have overall though, right? What is the sum of our bird spectros? $4,800. So we're going to do the similar approach of just creating 16 TF record files, each with 4,800 examples inside of them, because that's how many examples we have overall. But they're all going to be randomly selected. So there is a chance that, you know, one example might not be in there, and one might be in there multiple times. But it should be close enough. Okay. So running that task now. So we'll check back in just a little bit and see if we can train a model with that TF record file.